Hello everyone. So today we are going to do the 2010 January paper, and this is the second part and structured essay question. So we actually even I haven't gone through the questions yet, so I'm trying to create the exact exam situations here. So let us go through the questions together and try to find out the answers. I have the answer script as well. We will refer to that also. So we will read now. So this is the 16th question. It says magnesium chloride can be made by reacting solid sodium carbonate, which has the chemical formula uh, of this, with dilute hydrochloric acid. Write an equation for this reaction including state symbols. This is very important. Even if they haven't included, that's better if you write the state symbols as well. So you have magnesium carbonate and diluted hydrochloric acid. This is a carbonate. I'm going to use my Epic pen here. This is actually a good software as well, like if you want to use it. So this is a carbonate, right? I'm gonna close the vision. Okay, so this is a carbonate and this is an acid. So acid and a carbonate together will give you a salt. That's like a rule of thumb in chemistry. So we will go ahead and try to get the answer for this question. Actually it's better if you go to the okay. So you have magnesium carbonate, which is normally in the solid form, you see, and it's in the solid form here. And then you have diluted HCl, hydrochloric acid, which is in the aqueous form, meaning it's diluted in water, and this will result in this reaction, which will definitely give you carbon dioxide gas. That is the that is what happens when a carbonate and an acid reacts together, and of course you will get the salt and water as well. Water will be in the liquid form while salt will be in the aqueous form. So once you have written this equation, you're done with the or you're almost done with the chemical equation. The one thing that is left is to balance the chemical equation. So to do that, what you should do is count each of the atoms on the one side of the reaction and also on the other side of the reaction, and balance the atoms. So you have one magnesium atom here, you see, and on this side of the arrow and this side also you have one magnesium atom. So with magnesium you are okay. And then go ahead and count carbon atoms. So you have one carbon atom here on this side, and here one carbon atom. So with carbon also you are okay. Now we will leave oxygen for a while and then count Cl atoms. So in this side of the equation you have one Cl atom, and here you have two Cl atoms, so that is not balanced. For that reason you have to make this side 2 as well. That's why you have this coefficient 2 here. That means you have two chlorine atoms on this side with this 2 here, and that means you have two hydrogen atoms here on this side, and you also have two hydrogen atoms here. Oxygen 3 altogether, and on this side you have here 1, and with these two you have 3 oxygen atoms. Now your chemical reaction is balanced with the state symbol, so there's no reason why you shouldn't get full marks for this question, this answer. Okay, so you better write that, and of course you can use like anions as cations and ions as well, but this is a better version, plus it's really easy. So we'll move on to the next question. Okay. And the next question, you have been asked to give two observations you would make when the reaction is taking place. So now you know the reaction. What would be the two observations that you could see? So as you can remember, we got carbs bubbling up when the reaction is forwarding. Okay, that's going to be one, and the other one should be the solid disappearing, meaning you remember magnesium carbonate was a solid to start with, but at the end these are the results that you got. None of them has a solid in it. This is in the aqueous form, this is in the liquid form, and this is in the gaseous form. So there will be no solid at the end of the reaction. So the two observations should be the solid disappearing and the bubbling of carbon dioxide. You don't know if it's carbonate, we can just say bubbling of a gas and disappearing of the solid magnesium carbonate that was used in the first place. Okay, so in the part C, it says, in an experiment to make crystals of hydrated magnesium chloride, which has the chemical formula of this, magnesium carbonate was added to 25 cubic centimeters of hydrochloric acid with concentration 2 moles per cubic decimeter. The molar mass of magnesium carbonate is this much. How many moles of acid are used in this reaction? Okay, so your target is to find a number of moles. First of all, you better go through all the data that has been given. Here they have you need to find the moles of the acid here. So they have given the volume of the acid, of course, and of also what else have they given you? A volume and the concentration of the acid is given. How do you combine these two together? Okay, so if you remember the equation, number of moles if that is N is equal to concentration into volume. So if you really don't remember this equation, you can just get that by looking at the parameters here as well. So you have a volume here. See, volume, if you multiply that with the the concentration, which has the unit of moles and also inverse of a volume. So you have moles and inverse of a volume. Okay, so these two will cancel each other out, leaving you moles. So if you don't remember this equation, you can just use the units as well to find a certain answer. So the volume, which is 25, here you have 25 cubic centimeters. To make that cubic decimeters, you have to divide 25 by 1000, because the concentration is in per cubic decimeter, and then you have to multiply that by 2, which is the concentration, and that will give you the answer. Okay, so that's the number of moles, which would be equal to 5 into 10 to the minus 2, or 0.05. whatever you write it right there, you should get the full marks. We move on to the next question. What mass of magnesium oh yeah okay so what mass of magnesium carbonate in grams react with this amount of acid? So your target here is to find a certain amount of mass, that is magnesium carbonate in grams, react mm, reacts with this amount of acid. Okay, so hold on, I need to erase this. I'm wondering how to do that. Again, regarding magnesium carbonate, what are the data you have here? So magnesium carbonate okay, you are being given the molar that 0.05 moles of HCl was reacted was there in the mixture. And also from the reaction we wrote above, you know the stoichiometry between magnesium carbonate and HCl acid is 1 to 2. If so this is actually equal to 2, and since this is the acid, the carbonate should be 1. So if this is 2, then if you want to get the stoichiometry in this regard, you have to divide 0.05 by 2. That would give you the number of moles that would react with the given amount of HCl. So how do you find the mass of that? Again, if you remember the equation, this is really easy. N is equal to simple m divided by capital M. Simple M here is the mass given, and capital M here is the molar mass or the atomic mass or whatever. So your target is to find the amount of carbon that was reacted. So you need to subject that first. So simple M is equal to number of moles into a molar mass. Okay, so number of moles in regards to carbonate is 0.05 divided by 2, and into the molar mass, which is given 0.05 divided by 2, and all together into 84.2, which is the molar mass, which will give you the answer, which is 2.1 if you round it off. Okay, so that's the answer for that question. We'll move on to the next question. Suggest why slightly more than this mass of calcium carbonate is used. Why would you use in normally in practicality use little bit more than this? Why? I can just guess and write the answer. For example, maybe the magnesium carbonate is not exactly pure and you have impurities in, so to make up for that you need a little bit more. And also the best answer would be this, to ensure that all acid reacts. So if you add the same amount, due to many reasons, or maybe even human errors, maybe you can't exactly get that amount, and also we rounded off for so many reasons. Maybe some acid molecules could not react because there's no enough calcium carbonate. So to avoid this and to completely neutralize the HCl acid, we use little bit more than normally required. I mean that more than what you get from the calculation. Okay, so in the fifth one, how would you separate magnesium chloride solution from the reaction mixture? How would you separate magnesium chloride solution from the reaction mixture in 3? If you have unreacted impurities or anything, like you just go ahead and filter. This is one of the simplest separation methods that you learn. You can filter and separate the magnesium solution, and if you have good equipment you can centrifuge as well. You know what centrifugation is, just to insert the whole mixture into a test tube, and you can centrifuge, and all the heavy particles will sink down to the bottom, leaving the magnesium chloride solution for you. So just filtering or centrifugation, or yeah, or an appropriate separation method would be fine for that question. The next question asks, the magnesium chloride solution left to crystallize. The crystals were separated and dried carefully. The sample of 3.75 of hydrated crystals, which have the molar mass of this, was obtained. Calculate the percentage yield of this reaction. Okay, so okay, I need to calculate. Okay, so how would you answer this question? This is again is very easy if you know the equation for this. So the equation for this should be the percentage yield is the percentage yield is equal to the actual amount that you got divided by the theoretical. I mean, by calculation, what is the amount that you guessed you would get, that's this, and the actual amount that you got into 100, that is because they are asking the percentage yield. So in this case, this is going to be equal to the actual amount that you got was already given here. See, you have it there. So it's 3.75 in grams. And the theoretical amount, how would you calculate the amount? This is divided by, you have been given the molar mass. Again, you have to get this number, you're gonna have to do a separate little calculation if you can't get it through your head, like at once. How do you get the mass? What you need to do is you need to multiply the molar mass by the number of moles that was reacted, n, okay, that is the number of moles. So the molar mass here is, they have given 303.3 into the number of moles that were reacted. If you remember, it was 0.025. How do you get that? You got that the number of moles of acid was 0.05 and the number of magnesium chloride that you get is half of this according to the reaction. You can go back and refer to the reaction. So the number of moles in this case should be half of this 0.25, which is equal to 0.025. So once you solve this calculation, you will basically get 3.75 over an I think it's 5.08, and finally you will get the answer as 74. That should be your answer for this question. That's the percentage yield of this reaction. Okay, so we'll move on to the next question, and we'll see what you have there. Okay, so the next question is, give one reason why the yield of crystals is less than 100% even though you use pure compound. So it was 75%. Like this, some states in the solution. So basically that's that you were not able to collect all the salts in the solution, and some got lost while transferring from one content to another, and another one should be lost on the filtering because you use the filtering or centrifugation or whatever for the separation method, and while doing that process you could lose some of the salts and crystals left behind. You couldn't collect everything when you're weighing the crystals, and some left on the filter paper. Yeah, again, you know, when you're filtering, you're using a filtering paper that could absorb some of the actually considerable amount of the solution, if you're really concerned about the accuracy. Okay, so one of those should be good to go. And the next one, let's see, this is this regarding the same. Yes. Okay, so that question asks you lattice energies can be measured using Born-Haber cycle, of course, or calculated from the electrostatic theory. Lattice energies of magnesium chloride and magnesium iodide are given below. So you have the salts here, and this is magnesium chloride, this is magnesium iodide. Let me get my highlighter. I really like, sometimes really okay, so this is magnesium chloride, this is magnesium iodide. Lattice energy from the Born-Haber cycle is, when calculated you got this, and when calculated you got this. Lattice energy from electrostatic theory, you got this and you got this. The first question is, what does this data indicate about the bonding in magnesium and in magnesium chloride? So in this case you're gonna have to examine the data. So we will go ahead and examine the okay, so okay, but okay, you can write you can, for this question you can write something like this actually. That magnesium chloride, even though they have like very high percentage of ionic characteristics in their bonds, it's not 100%. It's always less than 100%. So this has little bit of covalent characteristics in it, so you can write something to give that idea. Here's the answer, something like not exactly 100% ionic, or it has little bit of partial covalent character, something like that. Explains why there's a great difference between experimental and theoretical lattice energies of magnesium iodide compared with magnesium chloride. So let's get back to the table here. Okay, this is magnesium chloride, this is magnesium iodide. You have a difference, and here also you have a difference. What could be the difference? Okay, so here the magnesium atom is the same in the both cases, so that can't, the reason cannot be due to the magnesium. It definitely has to be with the halide ion, so refer to that. So you can say magnesium chloride is little bit um, smaller smaller than the iodine, as it's higher in the periodic table than iodide. So this iodide ion is much larger. Since this is larger, it's easier to polarize, or like polarize this electron cloud. And so the iodide is larger, so it's easier to polarize or distort. Because the electron cloud is larger, it can be easily polarized than a smaller cloud. So that is the reason. We'll get to the next question. Okay, blood plasma typically contains 20 parts per million ppm of magnesium by mass. Calculate the mass of magnesium in grams present in 100 grams of plasma. Okay, so go ahead and just write the given data first, and let's see. Okay, so you have 20 parts per million. Million is 10 to the power 6. So per million you have 20. And how many per million? You have 20. This much of parts are there in a unit mass. Okay, if a unit mass contain this much, how much 100 grams contain? So do the calculations, and 20 divided by 10 to the 6 will give you 10 into 10 to minus 3. So that's the answer for that question. Let me, yes, this, okay. Oh, where's that? Okay, so magnesium, the next question is, magnesium chloride can be used as a supplement in the diet to treat patients with low amounts of magnesium in blood. So if you have a magnesium deficiency, magnesium chloride can be given medically. So just one property which makes it more suitable for this purpose than magnesium carbonate. So to get magnesium, why would you use magnesium chloride and not magnesium? Oh, that's right. Okay, so why not magnesium carbonate, and why magnesium chloride? This is really easy. Magnesium chloride more soluble because this is in the aqueous form, this is a salt, and magnesium carbonate is not soluble, mostly not soluble. It's okay, that something like that. Or your stomach is acidic, right? So if an acid react with carbonate, that will give you a gas which is carbon dioxide. So if you give magnesium carbonate, okay, so magnesium chloride is more soluble, blah, blah, blah. It can be given as a solution. It doesn't produce gas in the stomach. uh, yeah, doesn't produce CO2, something like that would give you the give you full marks for this question. So that's 8. And wait, I have to see if we check. I'm guessing this is the last question of that big question. Okay, yes, that's the end of that question. So I will do another video on this question, which is in the 2010 January paper. So you guys can check that out later as well. So thank you for watching, and don't forget to subscribe. And if you have any questions also, just post them in the comment section below. I will try to answer. Okay, see you, bye.